Hello, this is Math 2231 coming to you from the College of DuPage during the summer of 2020, and the title of this lecture is The Fundamental Theorem of Calculus, FTC. So we've been talking about calculus, which is the study of limits, and we talked about a special limit called the derivative, which is associated with the tangent line problem, and we've talked about another special limit, which is the definite integral, and that's associated with the area problem. Now these two problems might seem unrelated, but there's a very close connection. This intimate connection is more than a theoretically nice mathematical relationship. It is of immense computational significance. The area problem we solved earlier with complicated calculations becomes quite an easy exercise using the fundamental theorem of calculus. So, with further ado, let's quote the theorem. So, a fundamental theorem of calculus says, if a function lowercase f is continuous on the closed interval ab, and capital F, uppercase F, is an antiderivative of lowercase f on the interval ab, then the definite integral from a to b of f of x dx is equal to capital F of b minus capital F of a. Let's go back and talk about that example that we approximated the areas with, and also took the limit and actually calculated the area with. It's this one, but now we're going to do it using the fundamental theorem of calculus that we just quoted. So the definite integral from 0 to 2 of x squared plus 1 dx then is equal to, what I'm going to do is find an antiderivative of this. It will be done termwise. So the antiderivative of x squared is going to be x cubed over 3, plus the antiderivative of 1 is going to be x. And then I'm going to evaluate it at 2 and 0. This is notation that is pretty standard. So I plug in the 2, that is f at b, and when I put 2 in there, I get 8 over 3 plus 2. And then I'm subtracting this minus sign is from the theorem, f of a. Now when I put 0 in there for x, I get 0 everywhere, and that's equal to 14 over 3. You see that was much quicker. Now let's look at the proof of the fundamental theorem. And so the key to the proof, and there actually are two keys to the proof, but one key is writing this difference in a convenient form. So what we do is we pick a whole bunch of values of x to form our subintervals. We start at a equal x0 and xn equal b. And then what we do is, we're going to add 0 in a clever way many times. So this is f of b minus f of a, but we add 0 in a clever way many times. And I note that that can be written this way. That's the summation I equal 1 to n of f of x I minus f of xi minus 1. Now, the second key is the mean value theorem. So we know there exists a number ci in the ith interval such that f prime at ci, that's capital F prime at ci, is equal to, and this is going to be f at xi minus f at xi minus 1 all over xi minus 1. But you remember in the theorem we said that capital F was an antiderivative of lowercase f, so that means this derivative is equal to this. So you see all of these things that are in here can be written if we let delta x equal xi minus 1 in this fashion. So we have f of b minus a is equal to this, but this can be written in this fashion. So the first equals the third. Now this tells us that by repeatedly applying the mean value theorem, you can always find all of these c's, and so that's a Riemann sum. We're going to let the limit as n goes to infinity here. This and you see this doesn't depend on n at all, so that's still true for the limit, and so we get f of b minus f of a is equal to the definite integral from a to b of lowercase f of x dx. So here are some guidelines for using this fundamental theorem. Provided you can find an antiderivative of lowercase f, you have a way to evaluate a definite integral without having to use it as a limit of a sum. And so what you do is, we're saying that capital F of x is an antiderivative of lowercase of f of x. So the definite integral from a to b of lowercase f of x dx is capital F of x evaluated at a and b, and that's going to be f at a subtracted off from f of b. And so if we were doing this, the definite integral from 1 to 3 of x cubed dx, it's going to be x to the 4th over 4. You put 3 up there. You get that. The minus is from the theorem. You put 1 in and you get that. You do the calculation and you get 20. Note that it is not necessary to include a constant of integration in the antiderivative because you're going to be using the same antiderivative for the top and the bottom, and it'll just subtract off. So this means you can safely just use 0 for your constant when you're doing this problem. Okay, so here are some problems for you to do. You're supposed to evaluate each of the following. You know what to do. And we'll see how you did when we continue in 36.1.